In this lecture, we're going to take a closer look at the Euler Phi function. So what is this function? Well, it's denoted phi of n, and this is the number of, so it's the number of numbers less than n that are co-prime to n. So number of positive integers less than n that are co-prime to n. Co-prime to n. And as you'll recall from the previous lecture, this function came up in Euler's theorem. That's also why it's called the Euler Phi function. Euler was the mathematician who introduced this. So just to remind you what Euler's theorem says. It says that if I have some element of z mod mz that's co-prime to the modulus m, so if I have an integer a and it's co-prime to m is going to be the modulus, then there is sort of this magical exponent that you can raise a to in order to get 1. And that exponent is, it turns out to be phi of m. And we saw that this is a really important theorem because it indicates that powers, when you're mod m, powers are going to sort of cycle back to 1 every phi of m powers. Okay? This allows you to do computations with very large exponents relatively quickly. Okay. So in this lecture, we're going to investigate this function a bit closer. Going to discover, how to compute it and some properties of this function phi of m. It's a very important function in number theory. Just to do an example, so if you're computing this for small values, for example, let's do phi of 9. How do I do this? So I'd write out the integers from 1 to 9 and sort of go over each of them, check if it's co-prime to 9. And 9 is a fairly easy example because 9 is prime, not prime, but it's a power of 1 prime, which is 9 is 3 squared. So if I share a factor in common with 9, it'd better be 3 or a multiple of 3. So you can just cross those out, including 9 itself. And here's what's left. 1, 2, 4, 5, 7, 8. And the total count is 6. So phi of 9 is going to be 6. Okay. So normally when I come across a new function and I'm trying to figure out some properties of it or how it works, the first thing to do is just to generate some data. So let's make a little table and let's put n values of n across the top here and then phi of n across the bottom. So 1, 2, 3, 4. Let's go up to let's go up to 12. That's fine. Okay, phi of 1. So phi of 1, typically we want to define it to be 1. However, I'm noticing that this definition would actually indicate it as 0. So I think I do want to make one small change to this definition. I want to say less than or greater. Let me circle out. Less than or equal to n. So it's the number of positive integers less than or equal to n. Normally this is not going to matter at all, right? Because if n is greater than 1, it doesn't matter whether you say less than or equal, less than or equal. Because n is certainly not co-prime to itself, so it'll just always be crossed out. But I do want to define phi of 1 to be 1, so I'm just going to do that by changing it to a less than or equal. Phi of 2 is 1, phi of 3 is 2, that would be 1 and 2. Phi of 4, that's where it starts to get a little trickier. So phi of 4 is 2 as well, because There, I crossed out the ones that share a factor with 4. 2 left. Phi of 5 is 4. I know that because 5 is prime, right? So anything less than 5 is going to be coprime to 5. In fact, we have our first property of phi. So our first property of phi is going to be phi of a prime is going to be p minus 1. Just one less than that prime. Because anything from 1 up to p minus 1 is going to be coprime to p. So I count them all. So phi of 7 will be 6. Phi of 11 will be 10. Phi of 6, let's do that over here. So 2 shares a factor, 3 shares a factor, 4 shares a factor, 6 itself, of course, shares a factor. And we're left with 1 and 5. So phi of 6 will be 2. So notice how it's kind of jumping around a bit. It's going up and then down. This is maybe what you'd expect. So typically, most arithmetical functions are going to behave rather chaotically, especially if they deal with factorization or primes. Phi of 8 is 4. I'm counting 1, 3, 5, and 7 there. Phi of 9 is 6, as we computed already. Phi of 10 is 4. That'd be 1, 3, 7, and 9. Phi of 12. Let's try to write out the ones that are coprime to 12. So 1, 2 is not, 3 is not, 4 is not, 5 is coprime to 12. 6 is not, 7 is, 8 is not, 9 is not, shares factor of 3, 10 is not, 11 is. So it looks like I've counted 4. And this continues. Okay. And next thing I might do is stare at this table for a bit. And so usually when we have an arithmetical function, so this is an example of an arithmetical function. So it's just a fancy word for a function defined on the natural numbers, like that. Right, so when I have an arithmetical function, often the first question I want to ask is this a multiplicative function? So recall what that means. So a multiplicative function, so we say some arithmetical function is multiplicative if f of a product, mn, let's say, is f of m times f of n. But not always. We only demand that this property holds whenever m and n are coprime. Okay. And we saw some examples earlier, multiplicative functions, for example, tau, the number of divisors, sigma, the sum of divisors. We also saw mu, the Mobius function. There are plenty of multiplicative functions that we can cook up. And phi appears, at least upon first observation here, to be multiplicative. So whenever I take two relatively prime numbers, like 3 and 4, those are coprime. Phi of 3 is 2, phi of 4 is 2, and phi of 12, their product, is 4, which is what we would expect. 2 times 2 is 4. So that's an example. Phi of 12 is indeed phi of 3 times phi of 4. But notice it's not, phi of 12 is not phi of 2 times phi of 6. Phi of 2 is 1, phi of 6 is 2. 1 times 2 is not 4. But that's okay. So we don't need this to hold for a multiplicative function. A function is only called multiplicative if, whenever m and n are coprime, this property holds. So 4 is 2 times 2. This one's not necessarily true. And you can check some other examples. For example, 10, yeah, we have 4. 2 times 5 is 10. Phi of 2 times phi of 5 is also phi of 10. And in fact, phi does turn out to be multiplicative. So that'll be our theorem that we're going to try to prove. So phi of n is a multiplicative function. It is multiplicative. This makes it really nice to compute phi of n. So for example, if I had phi of, let's pick a large number, 36. Well, let's try to break 36 down as a product of coprime factors. So we could do 9 times 4. 9 and 4 are coprime. So really, to compute phi of 36, I just need to compute phi of 9, phi of 4, and then multiply them together. But these are small enough where we're going to use our table. So phi of 9 is 6, phi of 4 is 2. So phi of 36 should be 12, which indeed it turns out to be. So very useful that phi of n is multiplicative. Why is that true, though? So, before we try to prove this in a general case, let's look at an example and see how we might be able to prove this. So maybe this example here, actually. So phi of 12, let's try to show. So let's try to see why phi of 12 has to be phi of 3 times phi of 4. And right, so I think what I'd like to do is go back to, I'll redraw the chart here. So I had a chart in a previous lecture, and this was a lecture on Sun Tzu's theorem. So Sun Tzu's remainder theorem. I'm going to have mod 4 going across the top, and then mod 3 going across, going up the side here. So 1, 2, 3. That could be 0, 1, or 2 mod 3. And now the idea is I'm going to write out numbers 1 through 12, or I guess 0 through 11. Same thing if I'm mod 12. 0 through 11 in their proper locations. So 0 is 0 mod 4 and 0 mod 3. 1 is 1 mod 4, 1 mod 3. 2 will go there. Where would 3 go? It would go up here, actually. Right? It's 3 mod 4, but I'm back at 0 mod 3. And we discovered earlier that there's sort of a pattern going on here. The pattern is sort of go down and to the right. And you wrap around if necessary. So the 4 would actually go here. And then 5, 6, 7, 8 would wrap around. 9, 10, 11, like this. And, well, let's just verify. So does the 9 actually belong there? Yes, because it is 0 mod 3 and 1 mod 4. And Sun Tzu's theorem actually tells us that we will be able to fill in the entire grid like this, and we won't ever have to put the same number in. Put two different numbers in the same cell. So it basically says that every cell has a unique value of 0 up to 11. Okay. So in other words, we can solve any congruence. Like x is congruent to a mod 4 and b mod 3. There is a unique solution mod 12. It's just the corresponding entry of this table. So that's Sun Tzu's theorem in this case. Turns out, if you just stare at this grid, you can see this equation, which is really nice. So why can I see it? Well, let's suppose I have one of these numbers that shares a factor with 12. Okay, so suppose I have a number that shares a factor with 12. So let's say x shares a factor with 12. X is one of these numbers. So suppose it shares a factor with 12. Then, actually, x has to share a prime factor with 12. That's easy enough, right? Your factor itself is a product of primes, so just take one of those primes. 12. But 12 is 4 times 3, right? And if I have a prime dividing 12, which is 4 times 3, then that prime either has to divide the 4 or the 3. That's Euclid's lemma. Prime dividing a product has to divide one part or the other. And what does that mean? It means that my number will actually share a factor with 4 or with 3. Okay? But we can see in this table, where, let's take it the mod 3. So if I share a factor with 3, all 3 is prime, right? So the only way I can do that is if I'm 0 mod 3, if I'm divisible by 3. Let's cross those out. We're going to eliminate all of those. Okay. I just want to count. I want to count the things that are relatively prime to 12 that don't share a factor with 12. If I share a factor with 4, well then that factor has to be a 2 or some multiple of 2. And that means I'm either 0 mod 4 or 2 mod 4. Right? So these are exactly the numbers less than 4 that share a factor with 4. Okay. I'll cross out these columns. Okay. Anything that's 2 mod 4 is going to share a factor of 2 with 4. Anything that's 0 mod 4 is going to share a factor of 2 with 4. Factor will share a factor of 4. But regardless, we eliminate these columns and rows, and what we're left with, well, what are we left with? We're left with this little box here. So let's imagine eliminating those. We're left with 1, 7, 5, and 11. Right? Well, these are exactly, if I look up here, these are exactly the numbers less than 12 that are coprimed to 12. Okay, so we crossed out the ones that share a factor. And what's left? So, what are the dimensions of this square? It's 2 by 2. And why is it 2 by 2? Well, this 2 here came from the things less than 4 that do not share a factor with 4. In other words, phi of 4. That dimension is actually phi of 4, which is 2. And this dimension here is phi of 3. So numbers less than 3 that do not share a factor with 3, which is just 1 and 2. So dimensions of this little square here are going to be, so again, this is 2, and this is also 2. Dimensions of that square is 2 by 2, and the total number of numbers in the square is 2 times 2, which is 4. Okay, but really, what is that 2 times 2? That 2 times 2 is phi of 3 times phi of 4. And that was our way of computing phi of 12. Okay, because anything we didn't cross out is not going to share a factor with 12, because we cross out the ones that do share a factor of 12. And importantly, we realize that if we cross out something that shares a factor with 12, then we end up crossing out a whole column or an entire row, because of this Euclid's lemma, essentially. If I share a factor with 12, I have to share a factor with 4 itself or with 3 itself. If I share a factor with 4 itself, then that whole row is going to be crossed out, or the whole column. Okay, that's the idea. This basically is the same as... let me write out the general proof in any case. So, but it's basically the same idea. So suppose... this time we're going to start with n and m. Okay, so we're going to try to prove that phi of n, m. So, yeah. What does phi of multiplicative mean? It means phi of n, m is phi of n times phi of m if m and n are coprime. So suppose n and m are coprime, GC is 1. Then what we're going to do is we're going to create the same grid. So we're going to fill in the grid with 0, 1, 2, all the way up to mn minus 1, right? That's just like what we did here. So we have a huge grid. It's going to look like this. And like this. So here we'll go mod m. Here we'll go mod n. And I have 0, 1, 2, all the way up to finally n minus 1. And then 0, 1, all the way down to m minus 1. Fill in this whole grid. So 0, 1, 2, etc. How do we know we can fill in a grid? It's because n and m are co-prime, and we use Sun Tzu's theorem. Okay, so by Sun Tzu's theorem, every cell in the grid contains a unique value. Yeah, one of these values. Okay. Okay, and now we're going to take some number x, okay, belonging to this grid, and let's suppose that x shares a factor with the product mn. Okay. Then, here's the idea, x is going to share a prime factor. You go to a prime factor with mn. Let's call it p. And now we do the same thing. So we have a prime dividing the product mn. That implies, by Euclid's lemma, that p divides m or p divides n. So x shares a factor with either n or m. Okay. So I can sort of detect if x fails to be coprime with mn. I can detect that by just looking at n and m. Okay, and maybe it's, so I should be able to see it as it is not coprime to n or m separately. Maybe both, right? And maybe it shares a factor with both. For example, at 6 here. Yes, we conclude that x shares a factor with n or m. Suppose it's n. Okay, so suppose x shares a factor with n. Well then, this whole column here, so suppose x shares a factor. And when I say shares a factor, I don't mean 1, of course, something greater than 1. Shares a factor with n. Then this whole column shares the same factor. Why is that? Well, that just comes from modular arithmetic. So if I'm congruent to whatever this is, mod n, whatever number is there, let's call it y. If I'm congruent to y mod n, then this entire column, every entry here, is just going to differ by a multiple of n. Okay. So anything there is going to share the same factor that x and n share. So you can write it as a sum of x and n, or difference of x and n. Meaning I can cross out that whole column, just like I could do here. If instead it shared a factor with m, I would be crossing out the entire row. Okay. So we cross out the whole column. Okay, and then we repeat until everything remaining can do that, because there are finitely many things here, is coprime to n. Okay, so the key observation here is that any number sharing a divisor with n or m, well, if it shares a divisor with nm, it shares a divisor with n or m, and then it will belong to a wholly eliminated row or a wholly eliminated column. Okay. So the claim is that the remaining numbers form a grid, so a subgrid of dimensions. What are the dimensions? Well, again, so if x and n share a factor, then y and n also share that same factor. It's by modular arithmetic. So the remaining columns that aren't wholly crossed out, those will be elements that are coprime to n. So that's exactly phi of n. And the rows that are not crossed out, I've crossed out everything that shares a factor with m, so the ones that are not coprime to m. Everything left will be coprime to m. So dimensions, phi of n by phi of m. Okay. So there are phi of n times phi of m of them. And that proves it. So that proves that phi is multiplicative. Okay, just a couple points. So, actually, here's a really important point. So, where do we actually use the fact that n and m are coprime? It's actually not here, right? Euclid's lemma is true no matter if m and n are coprime, right? The key there is if you have to have a prime divisor. The place we used coprimality was actually Sun Tzu. It was Sun Tzu's theorem. If you remember before, so here's a really quick example. If we go mod 6 and mod 2, 0, 1, 2, 3, 4, 5, and 0, 1, and we try to do the same thing, where we fill in all of the entries. 0, 1. So we'll go from 0 up to 12. 2, 3, 4, 5. You notice we get stuck here because we want to put the 6 in the same place as the 0. Okay, so I really want to put the 6 here. And I want to put the 7 there, the 8 there, the 9 there, the 10 there, and the 11 there. Okay, but I end up filling in half the cells twice, and then the other half of the cells I don't fill in at all. Okay, so this whole proof breaks down. Right, we need to be able to have one element from 0 up to mn minus 1, because this is exactly what we're counting, right, with phi of n. So we need to have exactly one of these occupying each cell. Okay, so Sun Tzu's theorem is really the key of this. Is the key part of this proof. Okay. What next? So phi is multiplicative. Phi of n is multiplicative. And what we're going to do now is try to write a formula for phi of n. So this is the opposite of what we did with sigma and tau. Sigma and tau, we sort of deduced the formula first, and then from the formula we saw that it's multiplicative. Here we proved it's multiplicative first, and then we're actually going to use that to deduce the formula. So to find a formula, to find a formula for phi of n, it suffices to compute, because we already proved it's multiplicative, so it's the end of the proof. So it suffices to compute the following. We need to be able to compute phi of a prime power in general. Not just a prime, but a prime. We know how to compute it for a prime, right? It's just going to be 1 less than p. But we need to be able to compute it for a prime power. And that's because n is, we can always write it as p1 to the e1, p2 to the e2, etc., pk to the ek. And here's one way to break n apart into relatively prime elements. Just take each one of these. But we cannot break this itself into relatively prime factors. So we need to be able to compute it for an entire prime power. So that's our next goal. Let's figure out how to compute phi of a prime power. And luckily, that's not too hard. And the reason is, if we have something that's co-primed, let's do the opposite. So if we have something that shares a factor with p to the e, well, that, by unique factorization, it better be p, right? Has to share a factor of p. So all I need to do is write down all the elements from 0 to p, or you could even say 1 to all the way up to p to the e. It doesn't matter. Write down all the elements. There are p to the e of them, and then subtract out. So yeah, we'll think 1, 2, all the way up to p to the e. Now we're going to subtract out everything that's divisible by p. How many of those are there? How many things are divisible by p? Well, isn't it just going to be total number of things, which is p to the e, divided by p? So this thing here is the number of multiples of p up to p to the e. For example, if I'm doing, let's think through this. So if I want to do phi of 27, how would I do that? Well, I'd write down all 27 numbers, 1 through 27. But then every time I hit 27 is 3 cubed, so every time I hit a multiple of 3, I need to ignore that or subtract it out. How many multiples of 3 are there? Well, it's just going to be, 3 times 9 is 27. 9 is 27 over 3, so that's what I'm doing. So it's 27 minus 9. Oh, it's 18. So there's my formula. Should we write this in a nicer way? Maybe there are lots of ways you can write this. So it's p to the it's p to the e minus. See, this is just p to the e minus 1, right? If I want, I can factor out a p to the e minus 1. Get p to the e minus 1 times p minus 1. That's one way to write it. You can also factor out the whole factor of p to the e. And you get this, which looks a little strange, right? This is supposed to be a integer after all, so it looks like it could potentially be a fraction, but it's not. But yeah, these are all formulas. Usually I like this one the best. But this is a formula for phi of p to the e, which means, so since phi is multiplicative, it is a multiplicative function, we have a formula for phi of n. And it's going to be, so if n is this, it's just going to be a bunch of these. So it's p1 to the e1 minus 1 times p1 minus 1 times p2 to the e2 minus 1 times p2 minus 1 times, etc., all the way up to a final factor pk to the ek minus 1 times pk minus 1. And that's how you compute phi of n. This is one way to compute with phi of n. Let's do an example. So phi of 100. How do I do this? Let's write 100 as prime factorization, 2 squared times 5 squared. And now use the fact that it's multiplicative. So it's going to be phi of 2 squared times phi of 5 squared. So it's just this times this. So I'm just going to have 2 of these terms. So notice these are it's the term associated with the first prime, term associated with the second prime. And multiply these all together. So phi of 2 squared is, let me just write it all out just to make it very clear what I'm doing here. So it's 2 to the 2 minus 1 times 2 minus 1 times 5 to the 2 minus 1. It's 1 less than the exponent times 5 minus 1. And so we get 2 to the 1, which is 2, times 2 minus 1, which is 1. 5 to the 1, which is 5, times 4. 2 times 1 times 5 times 4 is 40. So phi of 100 is 40. Okay. Very nice. You might recall in the previous lecture, I computed phi of 100 another way. So another way. I should box it just to indicate this is an extremely important formula right here. Very important. This formula right here for computing phi. Okay. But there's another way to do this. So another way to compute, let's say phi of 100, is you can imagine writing down all the numbers from 1 to 100. And how many numbers are there? There are 100 of them. So phi of 100 is 100. And now I'm going to sort of sieve out the multiples of the various primes that are appearing here. Right? So again, if I have something that shares a factor with 100, it must share a factor with it must share a prime factor with 100, right? So it'll share either a 2 or a 5 with 100. And so I can just cross out the multiples of 2, cross out the multiples of 5. And I have to be a little careful, but let's cross out the multiples of 2. How many of those are there? There are, wouldn't it just be this? 100 divided by 2, so 50 multiples of 2. This is a number of multiples of 2. Less than or equal to 100. So crossing out 100 itself also, so you don't have to worry about me including the 100. And then this is going to be the number of multiples of 5. Less than or equal to 100. But here's the problem. I crossed out too much. So I'm actually crossing out, I mean, we can actually see back in this picture. So that's essentially what we were doing here even in this chart. We were crossing out multiples of 2, we were crossing out multiples of 3. And then we notice we crossed out certain numbers more than once. Okay, so if we're doing a count like this, here it didn't matter because they're already crossed out. We were just paying attention to what's left here. But if we're counting them in this way, in this count here, there are certain numbers that are included, both in this count and in this count. And we subtracted them out twice. We only wanted to subtract them out once, so we need to add them back in. And those are exactly the multiples of 2 and 5, which are the multiples of 10. So we add those back in. Multiples of 2 and 5, i.e. multiples of 10. And that's all we need to do. So we should get 40 again. Right? If we do 100 minus 50 minus 20, so that's 50 and 20, plus 10. Yes, we do indeed get 40. Okay, very nice. So this formula here is just a version of inclusion-exclusion. Inclusion-exclusion. This is a problem-solving technique where you include certain things and you exclude certain things that you want to exclude, but then you realize, oh, I've excluded too much. And then you include back in certain things, and maybe you've included in too much, and you exclude things again. And whenever we have some kind of inclusion-exclusion going on with the integer divisibility lattice, that suggests that the Mobius function is involved. So turns out that I won't prove this, but you might be able to see the idea. So phi of n can generalize this process here. We sum over. So I just want to sum over the divisors of 100. So that's like 100 over 1, 1, 2, 5, 10. And really I just want to sum over either divisors of 100, prime divisors of 100, or products of separate prime divisors. I don't care about 2 squared because that's entirely included here. Those have already been counted there. So I want to sum over divisors of n, and it turns out the right thing to do is, well, I do n over d, which is what I'm doing here, right? N over d, and the thing that gets me the right pluses or minus signs is exactly this Mobius function. This is a really important function in number theory. So mu of d times n over d. Let me remind you what this Mobius function is. So mu of n, there are 3 cases. It's either 0, 1, or negative 1. So it's 0 if n is not square free. And it's 1 if, so square free, essentially that means that all the exponents are 1. That would be square free. Okay, you can't have a square dividing n. So if it's not square free, then there's some exponent greater than 1. So this sum ei is greater than 1. And as soon as we have a ei greater than 1, mu of n is 0. So that automatically prevents us from including 100 over 4. Right? We didn't want to include that because it's just a power of 2. So the mu function automatically makes this turn out the right way. And similarly, so it's 1 if n is a product of an even number of distinct primes. And it's negative 1 if n is a product of an odd number of distinct primes. Okay? So odd number including 1, right? So if d is 2 here, it's mu of d here. So if d is 2, I'm going to get the minus sign. So I subtract out one term if I'm just looking at a single prime at a time. If I'm looking at 2 primes at a time, like the 10 is 2 times 5, I'm in this case, where n is a product of an even number of primes, 2 times 5. So the Mobius mu function just automatically gives me 1. It tells me to add those back in. So really an amazing function. This is multiplicative as well. Really a great function. And it comes up all over the place in number theory. In fact, this is a version of something called Mobius inversion, which is a very general statement about multiplicative functions. Yeah, this is a formula we have. And but in general, so why did I box this one earlier? I boxed that because it's often very useful to have a product formula. So this is a sum formula, and it's very useful for many things, but it's often very useful to have a product formula. And the reason why is if we know something about what this could be, then, for example, if this was some multiple of 7, if 7 divided this phi of n, well then we can actually start looking at this product and saying, well, wait a second, 7 is a prime. 7 would have to divide one piece of this product. So you know that either 7 is one of these, or it's one of these. And you can start deducing something about the number itself. So, maybe instead of saying this in words, let's do an example. So let's do the last example. So let's do an example. We will do... let's find all values of n so that phi of n is equal to 12. Okay, so how many numbers are there that have exactly 12 numbers less than it that are relatively prime? That's what we're asking. Okay. Did we see any already in our chart? Let's see. I don't think we did. Yeah, we got up to 10, but okay. So in general, these kind of problems are pretty complicated, but they're actually quite fun to think through. And 12 is small enough that I think we can think through it. So we're going to use this formula, the product formula, and we're writing 12 as a product. So 12 is going to be phi of n, which is some prime. I don't know what, but like this is just some prime divisor of n, right? It doesn't have to be a prime divisor of 12. Well, actually, it turns out it does, but because we're writing it as a product. But yeah, the meaning of p1 is just one of the factors of n. P1 minus 1 times P2, E2 minus 1, okay, etc. And now what we can do is, let's try to figure out something about n. So, there are lots of ways to do this, but I'm going to look at one of these terms, right? Because these kind of terms are always going to appear. We might not have anything here, right? If E1 is equal to 1, we're just going to get P1 to the 0. And so we just get P1 minus 1. But we're always going to have at least one of these. And so P minus 1, what can we say about, well, it has to be a factor of 12, right? So P minus 1 is a factor of 12. Let's start with the first prime. There might be a bunch of primes in this product, but we'll start with the first one. So this is a factor of 12. And that's all we know. It could be, this could be 6 here, this could be 4, it could be 3, it could be 12 itself, right? It could be 1 even. So there are a lot of possibilities. Let's look at all the possibilities. So P1 is either, like what if this was 1? It could be to prime 2, it could be to prime 3, it could be to prime 5. So it could be to prime 5 because 5 minus 1 is 4, which is a factor of 12. It could be to prime 7. It cannot be to prime 11 because 11 minus 1 is 10, which is not a factor of 12. So you just get a contradiction to this whole thing. So we can't have 11. So n is not divisible by 11. We already figured that out. It could be a 13, right? This could be, maybe that's our first case actually. Yeah, this could be 12 itself, right? None of the rest of the formula could be there. So let's actually start with that. So P1 could be 12. So yeah, let's say, sorry, not 12, 13. One more than 12. P1 could be 13. Well, that would mean that this term itself is already equal to 12. Right? So everything else has to be 1. So P minus 1 is already equal to 12. So this has to be 1. Like this term we have to include as part of this product, but this is okay. We could have E1 equal to, in fact, we have to have E1 equal to 1. If E1 were equal to 2 or more, we would get a 13 to the some positive power. So this would be too large. Okay, so E1 has to be 1. And then we, it might first appear that we can't have anything else. But we actually can have one additional prime here. Do you see how we could do that? Well, you could write 12 as 12 times 1. That would be the only way. But P2 could be the number 2. And then we could also have an exponent of 1, okay, to make this equal to 1. So E1 could be 1. And we could just be done, right? We could just have one prime factor. So we could have n equals just 13. But we could also have 2 prime factors. So this corresponds to P1 equal 13, E1 equaling 1. We could also have P1 equal to 13, E1 equal to 1. And we can add another term exactly this way. P2 could be 2. So 2 minus 1 would be 1. And E2 would have to be 1 because we don't want something there. that would correspond to n being 13 times 2, right? Both with exponent 1, so n would be 26. So we found two numbers here that have phi of n equal to 12. That's the only these are the only possibilities with the 13. So we're done with the 13. Maybe I'll do a little bit more and I'll let you finish it up. Because like I said, these problems are rather complicated. But it's pretty fun to think through them. So what if instead of the 13 we had the next largest prime, 7? What does that tell us? So let's look at this a little closer. P1 would be 7, okay? So you have 7 minus 1, that's 6. Can we have a 7 here? It's the same P1, right? No, because 7 times 6 would be much larger than 12, which is what our whole product has to equal. So the only possibility is if E1 is equal to 1. Okay. So again, E1 has to be 1. And our product so far is 6. Okay, we're allowed to have 12. But anything else, so anything after this, P2 to the E2 minus 1 times P2 minus 1. This has to equal 2. Okay, so 6 times 2 is 12. One way to equal 2, we could take P2 to be 3. And 3 minus 1 is 2. And then we're done, right? We already have a 2 and a 6, so E2 would have to be 1 to make this P2 to 0. And then seems like we're not allowed to take anything else, but we could do the same trick again, right? Where we could take a third factor and then include a 2. So P3 could be 2, and then 2 minus 1 will just be 1, so we're not actually making our product any larger. But then again, we would have to. So there's optional. Can include P3 to be 2 and E3 to be 1. So already we've produced 2 more values of n. So we're actually getting a lot of different values of n that have this Euler Phi function equal to 12. What are these values? Let's try to keep track of them. Okay, I kind of told myself I'd stop at the end of this page, but yeah, let's at least keep track of these. So n could also be, we could have P1 7, we could have P2 3, both with exponents of 1. So n could be 7 times 3, which is 21. Or n could be 7 times 3 times an additional 2 to the 1, which is 42. But there are more possibilities. So I'll let you, if you enjoy this kind of thing, try to continue through and think about all the ways that you can get this equal to 12. But every time you do, you produce a value of n. So these are the ones we found so far. I believe there are 2 more possible values of n. So it's a challenge to try to find them. Okay, well that'll be it for this investigation of the Euler Phi function. I should mention this function is also called sometimes the Euler totient function. Totient, I believe, is just a word meaning exactly this concept. It's all a number less than 9 that's relatively prime to 9 is a totient of 9. So Euler Phi function and Euler totient function, it's the same function. Okay, well that's it for this lecture. Thanks for watching.